So question number 2, a reinforced concrete beam has a simple span of 4.5 meter and carries a dead load of 200 kilonewton per meter and live load of 35 kilonewton per meter. Steel covering is 75 mm using F prime C equal to 28 megapascals and Fy 415 megapascals. In this problem, we are actually asked to determine the maximum moment due to the factored loads, the least dimensions using the maximum allowable reinforcement ratio, and the maximum area of the steel. Now, in order for you to determine the maximum moment due to the factored loads, we have to determine first the dead load and the live load. So for the dead load, we have 20 kilonewton per meter, and for the live load of 35 kilonewton per meter. Now remember, this dead load, this actually excludes the weight of the beam itself. So according to the book, the weight of the beam is actually approximate 20 to 25% of the summation of the dead load and the live load that it carries. So with that, we assume that 23% of the sum of the dead load and the live load is the weight of our concrete beam. So by that, so 23% times 20 kilonewton per meter plus 35 kilonewton per meter is equal to 12.65 kilonewton meter is actually the weight of the beam. That is just actually an estimation, an estimation of our of computing the weight of the beam. And in order for you to get the factored moment, we use this actually formula. So by this formula, we substitute the value of dead loads and for the live loads. So omega u is actually the factored moment is equal to 1.4 plus a times the dead load, which is the 12.65 plus the loads that it carries plus 1.7 times the live load, which is 35 kilonewton per meter, and we have omega u 105.21 kilonewton per meter. Now, in order for you to find the factored moment, we'll use this formula. Mu is equal to, or the moment, factored moment is equal to omega u times L squared, which is the span of our beam, concrete beam, over 8. So by substituting, we'll get 266.313 kilonewton meter. Now for letter B, we have to determine the least dimensions of the beam using the maximum allowable reinforcement ratio. Now we have this given formula. The maximum steel reinforcement ratio is equal to 0.75. The balance steel reinforcement ratio times the balance steel reinforcement ratio. Now we don't have this value, this steel reinforcement balance, the balance steel reinforcement ratio, and we have this formula to get that one. So the formula for the balance steel reinforcement ratio is equal to 0.85 times F prime C times beta 1 times 600 is over Fy times 600 plus Fy. Now, what is the value of this beta 1? Now, according to the book, if ang imuha daw F prime C is less than or equal to 30 megapascals, ang value doon nato is 0.85. However, kung greater siya, lahi ang ato ang gamiton dria, kanin dili siya 0.85. So with that, we use the value of 0.85 since the given F1 F prime C is 28 megapascal, which is less than 30 megapascals. So substitute. So the value for the steel reinforcement, balance steel reinforcement ratio is equal to 0.85 times 28, which is your F prime C, times 0.85 times 600 over 415, which is your Fy, times 600 plus 415, which is equal to 0.029. And to substitute this one, we'll get the value of our steel reinforcement maximum, the maximum steel reinforcement ratio, which is 0.0216. Now for continuation, in order for you to to get the least dimensions of our concrete beam, I will have to go through the step-by-step process as explained in the book or explained in our references. So first we need to get first the omega, which is the formula is equal to the maximum steel reinforcement ratio times your Fy over F prime C. So we have 0.4430. Now after that, we'll get the value of our moment, the factored moment. So we'll have to find the factored moment, and after finding it we'll have to get the value of our BD squared, since our B is actually the width of the concrete beam and D is actually the depth of our concrete beam, which is unknown. Both are unknown. So by mathematically speaking, so we'll have to find first this factored moment. So we have, since sa previous na ito nga nakuha, we have 266.313 kilonewton meter sa ito ang factored moment is equal to phi, which is according to the book, the value of phi is 0.9, and then our F prime C, which is equal to 28, and then omega, which is equal to 0.430, and then the BD squared, which is unknown, then times 1 minus 0.59, and then our W is equal to this one, 0.430, and we get the value of our BD squared is 32.93. Now in this value, we're able to assume that D is equal to 1.8B, or let's just say 0.55D, in order for you to get the least dimensions of your concrete beam. So with that, let's substitute our assumptions to this formula to get the value of our dimension that we are trying to find. So we have this formula, Rn is equal to factored moment over BD squared is equal to 266.313 over 32.93. So we have Rn is equal to 8.087 megapascals. So let's assume that D is equal to 1.8B, or B is equal to 0.55D. So by substituting, so let's use D is equal to 1.8B. So with that, 8.087, which is your Rn, is equal to mu, or the factored moment, over B times your D squared na 1.8B. And then by mathematical process, we'll get B is equal to 216.61 mm, which is practical because actually the least according to the specifications, the least width for the concrete beam is actually 6 inches or 15 centimeters. So with this, we're able to get 216.61, or let's just say in meter, that's approximately 22 centimeters. So that's the width of the beam. So by getting this the width of the beam, let's substitute this value to this formula para makuha na itong value sa ito ang depth of the beam. So we have 389.91 mm, or that's around 39 centimeters. Now for letter C, determine the maximum area of steel. So we have this formula, AS max, or the maximum area of our steel. Then we'll use the maximum steel reinforcement ratio, since the required is the maximum area of this. So we'll use the maximum steel reinforcement ratio, and then the dimension of the beam and the width and the depth. So by substituting, we'll get 1824.30 millimeters squared.